Okay, let's get started, as usual, with a quick review of previous lecture. So last time we started looking at the system architectures for the two main types of LiDAR, which is the direct detection LiDAR and the coherent detection LiDAR, or coherent LiDAR in short. And the main difference is basically the signal that you receive after the conversion from optical signal or photons to the electrical signal or electrons. So specifically, in direct detection LiDAR, these systems employ a simple photodetector. And as we know, the photodetector, the signal that you get out of it is proportional to the incident power or intensity of the light. So if you have some received basically signal waveform, which we call SR, which is the attenuation factor alpha times the delayed transmitted waveform, ST of t minus tau, times the Doppler shift, e to the j 2 pi fdt, we showed that as it passes through the photodetector, which is the photodiode plus the transimpedance amplifier in a coherent detection system, the signal that we get out, we call that SPD of t, is just some constant times the square of the transmitted pulse, which is delayed by the round trip time of flight. So you get some kappa times s squared of t minus tau. Remember the transmitted waveform ST itself was some generated waveform S of t times the carrier, e to the j 2 pi fc. So that carrier term also vanishes through this conversion effect. So we get a signal that is just a constant times the square of the transmitted pulse shape, which is delayed by the round trip time of flight. And as you see, there's no phase information. So it's a purely real signal. There's no phase information. It's intensity only. And because of that, these systems, all they can do, all the information they have, essentially from the signal that they receive, is this round trip time of flight tau. So they can only do ranging, but they cannot, for instance, measure Doppler shift and from that deduce or estimate the velocity. Then we started talking about the more advanced type of LiDAR systems, which is coherent detection LiDAR. And these systems, as we said, they employ a more complex optical receiver, which is called a coherent optical receiver. And coherent optical receivers, basically, what you get out of them is a signal that gives you is proportional to the full complex waveform that was transmitted. So again, if the input signal to the optical receiver, this is the same as the direct detection LiDAR. So because it's the same physics of wave propagation. So you get some attenuation factor times the delayed transmitted signal times the Doppler shift. And out of the coherent optical receiver, you get this SCR of t, which is some constant, times the full complex, basically, waveform, which is your signal delayed by the round-trip time of flight, or a waveform delayed by the round-trip time of flight, times the Doppler term, e to the j 2 pi fdt. So this signal model is identical to, for instance, what we had for CW radars. And from this, now we have information. So in principle, we should be able to estimate both the round-trip time of flight tau, which, as we know, is proportional to range, as well as the Doppler shift FD, which, as we know, is proportional to the relative radial velocity between the target and the LiDAR. So you get the full complex field where you have both phase and amplitude information. And today we'll see basically what type of waveforms the coherent LiDAR sends and receives, and then how the DSP works to estimate range and velocity, basically. So as you can see, coherent LiDAR is a more advanced type of a system. And it can, in principle, do more than just ranging. It can also measure the velocity. But today, most of the LiDARs that are deployed are direct detection. There are some coherent detection LiDARs also. But the reason is that's how basically technology works. More complex systems, they just have a longer, time to market. There's more R&D involved in the start. More complex systems are less robust, more expensive. So that's why direct detection LiDAR hit the market first, and now it has penetrated quite a lot in the market. But we are seeing, an uptick of deployment of coherent LiDAR systems, and that's why we study them. And then we also said, in terms of the waveforms of coherent LiDARs, it's kind of like what we looked at for the case of radar. So you can do frequency modulation, so you can have FMCW coherent LiDAR, which sends basically chirps as waveforms, linear frequency chirps, or you can have phase modulated systems that can use, for instance, ranging codes like PMCW radar or like CTFM sonar or similar to GPS as well. So the concepts should be very, very familiar by this point in terms of the type of waveforms and how each are processed. But we'll see there's some subtle differences in this case that we'll talk about today. Okay, so here's where we are. We're going to talk about the signal processing in coherent LiDAR systems today. And as we said, they're CW systems, so they continuously transmit a laser waveform. They can be frequency or phase modulated with periodic waveforms, very similar to CW radar. And we can build basically FMCW LiDARs or PMCW LiDARs. And the difference is in the types of waveforms that are generated and transmitted and received. Now, when it comes to the signal processing algorithms for coherent LiDAR, in principle, they're very similar to CW radar, but there are two main distinctions. One of them makes the DSP easier. The other one is a complication, but it's not too bad to handle. What makes it easier is that, as we know, the beam patterns for LiDARs, these are these Gaussian beams, which are extremely narrow and collimated. So most of the time, the return that you get, or the echo that you receive, is only from a single target, because the beam, spot size is very small, so it just hits a single target, comes back. It's kind of like you're pointing a laser pointer, out to the world. Most of the time, it's going to just hit a portion of a single surface. Unlike the case for radar, where, for instance, MIMO radars, if they use these microstrip antennas, as we know, they transmit very, very wide beam patterns. So the returns that you get are coming from, everything out there. You can get tens or hundreds of targets echoing back to you simultaneously, and that was a complication for the DSP. It's not the case for LiDAR. You can safely assume that there's just, one or a couple of returns. Okay, so that's the nice thing. The other thing, which is a complication for LiDAR, is that when it comes to Doppler shift, as we will see, the Doppler shifts experienced for LiDAR for the same target velocity are much larger than what a radar sees. So it could be 3 orders of magnitudes, for instance, larger Doppler shifts for the same velocity. And if you remember, for instance, when we were developing radar DSP, FMCW radar DSP, for instance, we used the fact that Doppler shifts were small. So specifically, we assumed that within one chirp time, we can ignore Doppler shift because it's much smaller than the frequency shift that is induced by just the range effect, and that we kind of baked in that assumption into our DSP development for radar. Now that doesn't hold for LiDAR, and we'll see today how we should handle that. So again, this is one of those cases where it's very, very important to know, when it comes to developing DSP, what assumptions are made and why they are made, and what they imply in terms of, what we can and cannot do. Okay, so before we look at the DSP, I just want to make a small note about signal attenuation. specifically in coherent LiDAR. So every type of sensor, active sensor we talked about, sonar, radar, and different types of LiDAR, in the signal model, there's always some attenuation factor alpha that we just, we added there, we didn't do much with it, okay? But for instance, if you want to estimate the signal to noise ratio of one of these systems, or if you want to run, physically accurate simulations, it's important to estimate what that alpha is, okay? Now, it turns out that although we didn't go too much into the details of it, in every case we have seen up till now, estimating alpha is kind of pretty straightforward. We kind of did it for radar. If you remember that radar range equation that we developed, that was kind of indirectly estimating this alpha. We also kind of did it for sonar when we analyzed, the full return signal model. So in those cases, if you refer back to how it was done, it's pretty straightforward. You just make assumptions about the forward pass and the return echo and the reflectivity or the cross-section of the target. So you just, it becomes a bunch of multiplications that you do, and that can give you, at the end of the day, with a round-trip signal path, how much attenuation you get. Now, when it comes to coherent LiDAR, it turns out that estimating or modeling this alpha becomes very tricky. So there's very deep physics that goes into it. And we can't quite get into the details of it because even, at a high level discussing why it becomes complicated to estimate alpha for coherent LiDAR, it requires knowledge of things like the speckle phenomena in optics and a concept which is called the backpropagated local oscillator, or BPLO. So it's way beyond the scope of this course or maybe any graduate course. It's a kind of a thing that, like, if you're doing PhD research on this topic, you would go and figure it out. But I just wanted to mention that it's not impossible, but it gets really complicated to estimate to correctly estimate SNR of coherent LiDAR. Okay, so with that, now let's start looking at the DSP of coherent LiDAR. And I want to start by looking at the Doppler shift, because I did mention that Doppler shifts in LiDAR are much larger than what a radar would see, and that becomes a complication for the DSP. So remember, the Doppler shift is given by this equation here. So minus 2 VR over lambda, where lambda is the wavelength, and VR is the relative velocity, relative radial velocity between the target and the receiver. So it's r dot, where r is the range, basically, from transmitter to receiver. Now, if we plug in some ballpark numbers for LiDAR, let's say you have a 1550 nanometer LiDAR, that's your lambda, and VR is 45 meters per second, okay? So it's fast, but it's not outrageously fast. I mean, it's a kind of a velocity you can easily get if you have some LiDAR in a vehicle or something like that. And then your Doppler shift turns out to be minus 58 megahertz for these choice of parameters. Now, for the same choice of velocity, if you calculate the Doppler shift for a 77 gigahertz radar, so that's just a different lambda, right? So your lambda becomes about 4 millimeters or so. Plug that in, your Doppler shift becomes minus 23.1 kilohertz, right? So notice the almost like 1,000x difference between the Doppler shift you get in LiDAR and the Doppler shift you get in a 77 gigahertz radar for the same velocity, right? So if you had the LiDAR and the radar on the same robot simultaneously measuring the same scene, the two can measure or see or experience very, very different Doppler velocities in the return signal. Now, because the FD is so much larger, the Doppler shifts are so much larger for the case of LiDAR, we cannot make the assumption we made for radar. So again, for radar, we made the assumption that the Doppler effect is negligible within every period of the waveform. And by every period, I mean, for instance, for FMCW, we said every one chirp that you look at, you can kind of ignore the Doppler shift. You just down-convert it, and the instantaneous frequency you get from one chirp is just proportional to range. And to find Doppler, we were looking at multiple chirps within a longer time period, which we called a frame. So that's what we did for radar. For LiDAR, we cannot do that, because even with such large Doppler shifts, even for one period of your waveform, if you just, again, if you're doing a FMCW LiDAR, if you just look at one chirp, within that chirp time, which could be just microseconds, the Doppler effect is so significant that it cannot be ignored, okay? So mathematically, now we need to solve for LiDAR a joint estimation problem. We need to simultaneously estimate both range and velocity, or both range and Doppler shift. It becomes a joint estimation problem that cannot be decoupled like we did for radar. Okay, so that sounds like a big challenge, but it turns out that folks came with a very smart trick in waveform design to solve this. And what they did is that what is common practice in FMCW, so now we're talking about FMCW LiDARs, frequency modulated coherent LiDAR. So in the case of radar, if you remember, the chirps that were transmitted, there were these sawtooth-like patterns in terms of like instantaneous frequency versus time. It would ramp up and then drop back to the start point and then go again. So it was a sawtooth pattern. Now for LiDAR, what you can do is that you can transmit triangular chirp waveforms. So within one chirp duration, you first ramp up your frequency linearly and then ramp it down. Okay. Mathematically, you can write it like this. So your entire chirp duration, if it's t seconds, you break it into 2 halves. Within the first half period, you send this waveform, e to the j2 pi fc plus b over 2 bt over 2 times t. So that's just a linear up ramp in frequency. And then in the second half, within one chirp period, you ramp down your instantaneous frequency. Okay, so then the time waveforms kind of look like this. As you see, it starts with a lower frequency. In the middle, it goes to a very high frequency, and then towards the end, it goes back down. So you kind of go up, go down in frequency. Instantaneous frequency versus time, as you see here, looks like these triangles. Okay, now. So with this, now something very interesting happens. If we look at now the received signal model with this choice of waveform, which is triangular chirps instead of sawtooth, signal model, we already know what it is. So in time domain, the time picture is this. So you send some waveform, that's a green one. Again, it's a triangular chirp. And what you receive is a delayed and attenuated and Doppler shifted version of this. Okay, exact same as FMCW radar. But if you look at the instantaneous frequencies of what you transmit and what you receive, now you have this very interesting picture on the right-hand side where the green is, again, what you transmitted. So you start at time 0. From 0 to t over 2, you ramp up on your green. And then from t over 2 to t, the second half, you ramp down. The blue is the instantaneous frequency of the received signal. And now two things are happening within just one chirp period. There is a round-trip delay tau, okay, so that we already know of, exactly like radar. But also notice that the blue is shifted also vertically. So the horizontal shift is your round-trip delay, but there's also a noticeable vertical shift because of Doppler, right? So the starting frequency of your blue is not FC, but it's FC plus F Doppler, right? Because you're Doppler shifted. So you also shift up, down according to Doppler, and it's non-negligible. This effect we also had for radar, but we just said the upshift is so small, we just ignore it, right? That's what we did for FMCW radar. Here for LiDAR, we cannot, right? So it's not that the physics changed. Right? The physics is the same. We had this effect for radar also, but it was so small at those frequencies that we ignored it. Here we cannot ignore it. Now, if you calculate the difference between the instantaneous frequency of what you transmit and what you receive with this triangular choice of chirp waveforms, as you see, during the up ramp of the two waveforms, you get some difference delta F1. And during the down ramp, you get a difference, a different value of delta f. We call that delta f2, right? One could be smaller, the other one could be larger. And it turns out that if we somehow estimate both delta f1 and delta f2, from that we can calculate both range and velocity, okay? And that's all we need to do. So let's see what the signal model looks like with this choice of waveforms, and then we'll see the DSP. So just how the FMCW LiDAR uses these signals. So it feeds the transmitted chirp signal as the LO input, or the local oscillator input, to the coherent receiver. Okay, so the coherent receiver, remember, has two inputs. The LO input is basically the field amplitude times the transmitted chirp, given by this, and the second input to your coherent receiver is just the received basically optical field, which is the attenuation factor times the field amplitude times the delayed carrier times the delayed transmitted chirp times the Doppler shift, right? Every term should make sense in this. Now, these two, basically, we know the coherent receiver, it kind of works like the down converter for in RF. So it basically extracts, you know, the conjugate multiplication of the two inputs that you feed to it. So we can solve that. So we can basically find the coherent receiver's output signal, and just if I go back, so we're going to break it because there's an up ramp and a down ramp. When we want to calculate the output of the coherent receiver, we can break it into two calculations. So first we look at this part, the up ramp part, which is from tau to t over 2, okay? And that's where there's a frequency difference delta f1. And then we look from tau over, from t over 2 plus tau, so this would be t over 2 plus tau to t. So we look at this portion then, and that's where there's a frequency difference delta f2. Okay, we do that separately, so the math is just more tractable. Okay, so let's look at the first part. So that's the, remember, that's the up ramp part of the transmitted and received signals. And what comes out of the coherent receiver is some constant times the received waveform times the conjugate of the transmitted waveform. Okay, this is exact same as radar, so I'm not going to go over all the steps. We know how this works. There's two basically complex exponentials that get multiplied out for the chirps, and then a bunch of terms cancel out. At the end, once you simplify it, it becomes equal to some constant, call that mu tilde 1, times a complex exponential, which is e to the j 2 pi delta f1t, as expected, right? Just from the visual inspection, we expected this SCR to have some frequency delta f1. But what's interesting is that delta f1 is equal to your Doppler shift minus b times tau. What is b? B is the slew rate, and tau is the round trip delay. Okay. And then mu tilde 1 is just some complex number. Doesn't really matter. It's a constant, right? There's no time dependency for it. Now, if you look at the second half, basically the down ramp part of the transmitted and received chirp. So that's where tau is between t is between t over 2 plus tau and t. And you do the same thing. Again, the signal you're getting out of the coherent receiver is a constant times received signal times the complex conjugate of the transmitted waveform. And again, you do the simplifications. It's very straightforward math. It's multiplication of two complex exponentials. But after simplification, what you get is some constant times e to the j 2 pi delta f2t. And here your delta f2 becomes the Doppler shift plus b tau. Okay, now compare these two. And you see one of them is fd plus b tau, one of them is fd minus b tau. So if we estimate delta f1 and delta f2, very easily from that we can find both tau and fd. You just add them and divide by 2. That's your fd. and you subtract them and divide by 2 times b, that's your tau, right? It becomes a linear system of 2 by 2 equations. Any questions so far? Okay, so now we have the full received signal model. Again, let's look at it graphically. So it's the math was a bit dense, but this is the same picture we had, the transmitted and the received signals. They get fed into the coherent receiver, and this SCR of t that you get out, if we look at the instantaneous frequency of that signal, it's equal to some value delta of 1 between tau and t over 2, right? That's the first part. That part, let's call that SCR1 of t, okay? So that's just mu1 e to the j2 pi delta f1t between tau and t over 2. And then from t over 2 plus tau to t in this part, that's where we have SCR2 of t, which has an instantaneous frequency delta f2. Okay, and that's our SCR2 of t. And what are the instantaneous frequencies? Delta f1 is fd plus b tau, and delta f2 is fd plus b tau. Okay, so now with this, now that we know exactly the signal model that we get out of the coherent receiver for this specific choice of waveform, which is the triangular chirps. Now what we basically have SCR1 and SCR2. And if we estimate the instantaneous frequencies of those two portions, they're just two portions. I'm calling them 1 and 2, but it's one time series signal that's coming out. But first half it's called SCR1, second half we call it SCR2. So we kind of break it into two shorter, basically, time series signals. But the point is, if we estimate the frequency or the instantaneous frequency of these two, from that, we get delta f1, delta f2, and then from delta f1, delta f2, we can, with very simple, algebra, we can get the Doppler shift and the round trip delay or the range. How do we estimate frequency? Same as we have done before for radar and sonar. Simplest algorithm is what? It's the Fourier transform. Okay, so here we need to do two Fourier transforms because we have two portions of the signal. So you kind of like separate them out, and it's done on the digitized signal, of course. So it passes through the ADC. We get SCR1 of n and SCR2 of n. This is the discretized version of the signal out of the coherent receiver. And note that this is just one received chirp, right? So unlike the case of radar, where we had to, build these big data matrices or data cubes for MIMO systems, and then, process a whole frame, for LiDAR, it's easy. It's like one chirp in, one target out, one chirp in, one target out. So it's much shorter, much smaller signals you need to process. So you do your SCR1, SCR2, do an FFT on each of them, and then you get SCR1 of k, SCR2 of k out of the FFT, and then you look for peaks in the FFTs, right? The expectation is, again, because most of the time, for each chirp, you're just getting returns from one target, each of these FFTs should show one peak, right? Very rarely you can get returns, partial returns from multiple targets, and that's a complication that cannot be easily handled for FMCW LiDAR, but it's safe to assume almost always you just get one peak from each of these FFTs. So here I'm overlaying the two plots of the two FFTs in red and blue for SCR1, SCR2, and each has a peak. One of them, call that the peak index, call it k hat 1, and the other one called the peak index k hat 2. Because the Doppler shift can be positive or negative, the period of the FFT that we took, we take it symmetrically, so the indices can go from minus n over 2 to n over 2 minus 1. So we look at both positive and negative frequencies when we are searching for k hat 1, k hat 2. And as we have done for radar, we can map the indices in the FFTs to the actual delta f frequency. So the delta f, the frequency corresponding to each of these peak indices, is just the k hat divided divided by the number of points in the FFT times the sampling rate. Yes?
Do you, for like, at these frequencies, like, how do you get rid of, like, there's still, like, the constant, like, carrier term when you mix it?
The carrier term goes away in the coherent receiver, so it gets basically mixed down to baseband. If you want the full derivation of how that happens, it's in the notes. I'm just gonna refer you to, if we start here, where we start talking about the optical coherent detection. We go through the full thing, from the ground up. Basically, we build the full model for the optical coherent detector. But the point is that at the end of the day, that signal, where is it? It's here. The full signal that you get, the carrier term is canceled out, but the Doppler term remains in it. Again, exactly like a down converter in RF. So it brings the signal down to baseband. I mean, baseband plus Doppler, basically, but the carrier vanishes out of the coherent receiver. Okay, so that's it, right? So you do break the signal into two sections, do two FFTs, find peak, you get your two peaks, and map the indices of the two peaks to frequencies, and then you have your basically delta f hat 1 and delta f hat 2 out of the peak search. Okay, so how do we find range and velocity now that we have the two delta f's? Very simple, right? Because remember, we had something like delta f1 was equal to fd, I think, minus b tau, and delta f2 was fd plus b tau, right? Double check this, but I think that's what we had. So if you want to find, for instance, tau, or tau hat, becomes equal to delta f2 minus delta f1 divided by 2b, right? And r, or r hat, is just c times tau hat over 2. So if we plug that in, it basically becomes c times delta f2 minus delta f1 divided by 4b. Or if you like to write it in terms of the indices of the peaks in the Doppler, you can also do that. And that's the expression, c times the sampling rate times k hat 2 minus k hat 1 divided by 4nb, where big N is the number of points in the FFTs that we took. So that's your range in meters. And just like that, you can find your relative radial velocity, which, as we know, is minus the Doppler shift times lambda over 2. And then what is the Doppler shift? Fd, or f hat d, is equal to delta f1, or delta f hat 1 plus delta f2 divided by 2. So plug that into here. You get lambda plus delta f1 plus delta f2 over 4. Or again, if you like, you can write it in terms of the indices of the two peaks in the two FFTs. And that's your velocity in meters per second. Again, the main assumption we made here is that because the Gaussian beams are very narrow, we assume that each received chirp contains echo from at most one target. Or in other words, the assumption is when you do these two FFTs, each of them has at most one peak in it. It can have no peaks if there was no return, but we are assuming at most one peak. It can happen that rarely they have a couple of peaks in them, and then that becomes an ambiguous case because you cannot establish correspondence between the two peaks in one FFT and the two peaks in the other FFT, basically. And in those cases, at least with this setup, you cannot find the two targets unambiguously. Questions? Okay, so this is it. The DSP for FMCW LiDAR is essentially much simpler than FMCW radar, and for two reasons. One was a smart choice that has been made for the choice of waveform. This triangular, waveform really solves this problem of the strong coupling between the Doppler shift and the time of flight delay. If we were to work with sawtooth chips like radar, it would have been much more complicated. But also the second thing that made it really simple, the DSP, was the fact that it's just one return or one target you're looking at, so per chirp, so you just process one return chirp at a time, and you know, a lot of the complications associated with radar, for instance, FMCW radar, just don't happen. Like, you don't need to work with these large data cubes and so on and so forth. Okay, very quickly, you can also find the minimum range and velocity discrimination, or range and velocity resolution, if you will. And as we know, exactly like the case of radar, when your frequency estimation algorithm is a FFT, the minimum frequencies that you can discriminate is one FFT bin, right? Another way to think about it is if you look at, if I clean things up here, if your R is given, for instance, by this expression, the minimum, discrimination in range is when, for two different targets, is when k hat 2 minus k hat 1 is equal to 1. And that means the two targets are just one FFT bin away from each other. So you can find your delta R min, which becomes equal to, again, you plug in the width of one FFT bin, which is Fs over n, into your R equation, so becomes C times Fs over 4nb. Or you can write it in terms of the total chip bandwidth, which becomes C over 4b. Remember, the total chip bandwidth for these triangular chirps is, because we use only half of the full chirp duration to ramp up, right? So if you start at some frequency fc, you go up to fc plus bt over 2. So your chirp bandwidth, which is the total, frequency range that you sweep, is big B equals bt over 2. For the case of radar, because it was just one op-ramp, your chirp bandwidth was B times T. There was no over 2, but here you have the chirp bandwidth for the same duration and same slew rate, basically. And that, if you compare this to what we had for radar, you would see that there's a factor of 2 difference. That's why, because the bandwidth you get, again, for the same slew rate and same chirp duration is half in this case, because you need to ramp up and ramp back down. Velocity resolution, same thing. You just, the velocity equation we had in the previous slide we derived, you just look at that for how much that changes when you change your peak by one FFT bin, and that's your delta V, and it becomes lambda over 2t and meters per second. The trade-offs are the same exactly as FMCW radar. So if you want more velocity resolution, for instance, what should you do? Increase B. So delta R goes down, you get, more range resolution. So that's more range resolution. If you want more velocity resolution, what can you do? Increase chirp duration, or go to shorter wavelengths, for instance. And that's what you can do. What about maximum unambiguous range and velocity? So in this case, they are coupled. So unlike the case of radar, where we had one FFT for range, one FFT for velocity, here the same FFT essentially gives you both range and velocity information. So you cannot independently determine your unambiguous range and velocities in this case, again, because the peaks that you get, the frequency of them has contributions from range and from velocity. But the point is, for a given FFT, the maximum peak frequency you can find in it, delta F max, is half the sampling rate. Why half? Because we look at it two-sided. So we search for delta Fs that are between minus Fs over 2 and Fs over 2. And because of that, the maximum peak in each of those two individual FFTs that you're doing, the maximum frequency for the peak is going to be Fs over 2. And that's the maximum detectable frequency. What range and velocity translates to? Well, it depends. If everything is stationary, then all of that delta F is contributed to from the range, and then you can say in a stationary world, this is the maximum range I can sense. Or the other way around, if you're sensing something very close to you, but it's moving very fast, from this you can maybe determine what's the maximum velocity. But they're coupled, right? So you cannot independently say maximum range, maximum velocity, because they get coupled through this. Questions? Okay, so this is it about FMCW LiDAR. You can also build PMCW LiDAR. And we know exactly how this is going to work. It's the same physics, same architecture, different choice of waveforms and DSP, right? Now, before we talk about this, we are not going to go into a lot of depth here because, PMCW LiDAR, to my knowledge, it has not been commercially deployed yet. Although it's a very, very interesting technology in research, there's a lot of very interesting research being done on it. For, some technological reasons, mainly because it requires, ADCs with very high sampling rate, and the DSP gets a little more complicated, it has not been commercially deployed. Now, that's today. I'm sure, well, not 100% sure, but I'm fairly confident in a few years we're going to see PMCW LiDARs deployed. So it's important to at least know the concept, and so if you decide to work on it, or if you encounter it later in your career, you kind of know what the ideas behind it are. Again, main difference here is they use different waveforms. And specifically, they use ranging codes, and they're phase modulated. So binary phase modulated, BPSK modulation, again, exactly like PMCW radar and GPS. And the waveforms that they send, you can send any codes basically with good autocorrelation properties. Most common one is MLS or M sequences. So that's your underlying waveform, and then you phase modulate it, and you get basically a sequence of plus and minus ones, exactly like GPS, that multiplies your carrier. So this first term is the BPSK modulated waveform, which again is just +1 and -1s, and then that's your carrier term. So in time domain, basically, this is what it looks like. One code word is just a series of +1s and a -1s that are multiplying the carrier. So every time you go from a +1 to a -1, you get like a 180-degree phase shift in your carrier. Okay, so that's the signal, and then the signal model on the receive side is exactly the same as FMCW LiDAR because it's the same physics. So the signal you get out of your coherent receiver is some constant times the delayed transmitted waveform times the Doppler shift. Okay, so you get attenuation, you get a delay, and you get Doppler shift. Okay. Then you need to digitize this and do DSP on it to recover range and velocity, or range and Doppler. Now, in the case where there is no Doppler shift, if FD is 0, we know exactly how this is going to work. You have transmitted some code, you have a received code, which is delayed and attenuated with respect to the transmitted code, but there is no Doppler shift. So all you need to do is just take the cyclic correlation of the two, exactly as you've done in GPS, and then that correlation shows a peak at the round trip delay tau. Okay? Very easy. We all know how this works. But it gets kind of complicated when you have Doppler shift, because as we know, for the case of LiDAR, Doppler shifts are pretty big and non-negligible. So you have to either cancel out the Doppler shift, or jointly estimate it with range, or do something about it. Now, in this more general case where there is Doppler shift for PMCW LiDAR, there's no standard algorithm as of today. Okay, again, because this is still being researched, there's ideas out there, and some of them have been proven experimentally, and we know they work. But there's no, like textbook standard algorithm that you have PMCW LiDAR. This is what you do, step 1, 2, 3, and it works. Okay, so I'm just going to mention the ideas or some possible approaches to how you could do DSP for PMCW LiDAR in the general case where you have Doppler. First idea is exactly the same thing we did for GPS, right? This was also a problem for GPS. Remember, GPS, you had to jointly kind of estimate your range and Doppler, or the way the GPS receivers work, it would basically search for the Doppler shift, and once they kind of found it, they would cancel it out by doing Doppler demodulation. And this should all be familiar because that's how the GPS worked. So you can do that, somehow estimate your Doppler and do demodulation with it. And then after you demodulate your Doppler, you get something that is only a delayed coding range, a range encode, and then you just apply a correlation to that and do range. So that's basically do it the GPS way. That's one idea. Other ideas that are quite interesting, and I've linked some research papers here. One is there's some algorithms in DSP which we can jointly estimate range and Doppler. Pretty interesting. So you just formulate it as a joint, optimization problem. Or another very interesting research track is, well, you don't have to transmit M sequences. You can design more mathematically advanced waveforms, which, for instance, still have good autocorrelation properties, but they're robust to Doppler shift. So when you get Doppler shift on them, it doesn't destroy the correlation properties as happens for M sequences. And that's a very, very interesting research topic of, what kind of special range encodes you could do. This area of, code design is also, it's not just for LiDAR, even for GPS. Still today, there's very active research being done, in new waveforms, new code designs. So a couple of days ago, there was a PhD defense here at Stanford that was about new code designs for GPS, which was very, very interesting to me. So just so you know, it's a very active research area, and you can do very, very interesting things in this domain. Okay, so that's it about basically coherent LiDAR. So we developed a signal model. We talked about FMCW and PMCW signal processing and waveforms to do range and Doppler estimation. Next topic is direction of arrival or DOA estimation for LiDAR. But before we start that, any questions? Okay, so DOA estimation, I mean, we have kind of talked about it. It's extremely easy for LiDAR because it doesn't require DSP, essentially, or maybe very minimal DSP. We should talk about the two main types of LiDAR. So if you remember, there's flash LiDAR, which illuminates the entire scene, in one shot with a very wide laser pattern. And there's a scanning LiDAR. Okay, now let's look at how DOA is estimated in flash LiDAR. So in flash LiDAR, it's pretty easy. So on the receive side, we have an array of photodiodes, kind of like a camera sensor, right? It has multiple pixels, and then it has some optics in front of it. And then on the transmit side, they transmit a very diffuse wide laser beam that illuminates a very large area in the scene. And then the receiver essentially takes an image of it, if you will, except instead of a RGB image, it's a time of flight image. So every pixel measures time of flight. But just by looking at the way the optics work, every pixel in a receiver array of the flash LiDAR, it basically gets returns from a very specific direction in the scene, which is like if you look at pixel J, the theta phi, which is the azimuth elevation angle of the returns that pixel gets, is fixed in the scene. Again, exactly like camera, right? That's how images are formed. Every pixel in your camera, you can trace back the direction of the rays that hit it from the scene. And the way that is done, you can just connect the pixel to the optic center of the lens and just trace that ray. So with ray tracing, you know exactly where the direction of arrival of every pixel is. And for as long as the optics is fixed and the placement of the photodetector array relative to the optics is fixed, that the direction doesn't change. So you just basically have like a lookup table that tells you every pixel what the DOA associated with it is. And that's how you do DOA. There's no DSP required for flash LiDAR. Okay, it's just by geometry of the pixels and the optics and, you know, their geometric relationship between the two, which is the distance basically. Okay, what about scanning LiDAR? Scanning LiDAR also, it turns out that you almost don't need any DSP. It kind of depends on the scanning mechanism, and we know there's like different scanning mechanisms. But basically, again, because we're sending out super collimated, you know, pencil-like laser beams, the DOA is the direction that the beam scanner is pointing to. Okay, so we kind of know the DOA. We don't need to, you know, estimate it from the returns like we had to do for radar. So here's one example for a multi-beam spinning LiDAR. So those are the ones that we had one in class last time, and we looked at it. We know they transmit multiple laser beams simultaneously, and each of the beams coming out is pointing to a fixed elevation angle. So those are fixed and never change. So basically the phis are determined by the position of the lasers. Here's how you can look at it. So inside the LiDAR, basically, you have a stack of laser diodes and a stack of PDs. Okay, so they're literally, you know, stacked on top of each other. And each of them, when it transmits, there's usually, they are pointed backwards. It hits a mirror and then comes out and goes through the lens. And then there's two lenses, one for the transmit, one for receive. So if you look at your laser diodes, because they're stacked, and then there's a lens in front of them, each of them will point to a fixed elevation angle. It has a fixed phi. And there's very precise alignment between the photodiodes and the lasers, so that there's correspondence. Like first laser, it points in some elevation angle phi 1, and the first photodiode also is looking at the same elevation angle. So the beam that was transmitted by the first laser, the echo from it is received by the first photodiode. That's such that there's, you know, no cross coupling between the multiple laser beams and their corresponding returns. So you have the two stacks, and it could be like any number between 16 or 128, you know, typically lasers and receivers, and each of them, the elevation angles are just fixed in hardware, never change. Okay, what about azimuth? Well, the azimuth, we know these systems spin around 360 degrees. So for each transmitted pulse, you kind of, by looking at the position of the motor, you also know the azimuth angle. And you just read that back from, say, an encoder that's on the motor, and that gives you your theta. Okay, so the phis are fixed per laser or per PD, and the theta, you just read it back from your motor. And that's how you do DOA in a multi-beam scanning LiDAR. Pretty much no DSP again. It's very simple. I mean, the DSP is just read back the state of the motor and see what angle that is. Okay, one more example for scanning LiDAR. Again, there's lots of different scanning mechanisms, but the idea is the same. So for other scanners, here's like a MEMS one, where it scans in both azimuth and elevation. Again, usually you have like a model for the scanner. And what the model does for you is basically it tells you the azimuth and elevation angles, theta and phi, of the outgoing beam with respect to the state of the scanner. What do we mean by the state? Well, it depends on the scanner type. But here, for instance, for the MEMS scanner we are showing here, the state could be, you know, the the state of the two actuators, one of which controls the pitch and the other one controls the roll of the mirror. And if you have some geometric model of this, pivoting mirror, by reading back the state of the two actuators, feeding that to your forward model, that tells you the theta and phi of the outgoing beam. And that is basically your DOA. Another example of this, for instance, for a two-galvo system, I think last Friday went over the full details of how you can build that geometric model for a complex beam scanner that has two mirrors. If you didn't tune in, make sure you look at the recording, because it's a very important, very interesting example of how you can build these geometric models that tell you the DOA for a specific choice of beam scanner. Okay, but it's a modeling effort. It's not DSP. It's not dependent on your received signals. You just model it once and use that model. Always just feed the state of the scanner into your model, and the model predicts the angle of the outgoing beam. But it's important to build the model, because if you don't build the proper model, you can get distortions in the point clouds that you reconstruct because your theta and phis are not accurately calculated. And that's it. So DOA in LiDAR, it's very simple generally, or in comparison to radar, I should say. It's much simpler. There's no added DSP overhead, but it requires accurately modeling whatever beam scanning method you're using, and using proper models so you don't get distorted point clouds. Okay. So we're pretty much done with the discussion of LiDAR. Just to recap, let's look at the end-to-end DSP pipelines for different types of LiDARs we discussed. So starting with the direct detection LiDAR, so you get the signal out of your photodetector. And as we know, the way it can only estimate range, right? And the way ranging works is that it does the leading edge detector or leading edge thresholding, and from that it estimates the tau hat, or the round trip time of flight, and you can convert that to range, so you get R hat. And for DOA, you basically get that from your beam scanner, either read it directly back or from the model that you have. That gives you your theta hat, phi hat. And from the range and the azimuth and elevation angles, you can now build 3D representations in the form of, say, a point cloud, for instance. And that is the final LiDAR image that comes out. Okay, so that's your direct detection LiDAR. Coherent LiDAR, let's say FMCW that we just talked about. So you get your signal out of the coherent receiver. You kind of break it into the two halves. We call that SCR1, SCR2. It's the two halves of the same signal. You do FFTs on the two, and then you find the peak in each FFT that gives you your delta F1 or delta and delta F2. And then by some very simple math on delta F1, delta F2, as we know, you can estimate range and relative radial velocity. And then the DOA, again, you read it back from your scanner if it has read back, or if not, you have some forward model, and from that you just estimate what the pointing angle was for your beam scanner, and that is your theta hat, phi hat. And now you have range, velocity, and DOA, and then you can produce representations, usually in the form of a point cloud, and that's your output LiDAR image. What about coherent PMCW LiDAR? It's slightly more complicated, so you get your signal out of the coherent receiver. There's different methods, as we said. Here I'm showing the case where you somehow estimate your Doppler shift, and then if you have an estimate of F hat, you can demodulate your signal with the Doppler. So basically, exactly like a GPS, multiply it by minus j2 pi F hat d. And that's now this S tilde of n is the signal with Doppler canceled out, so you can just correlate that. Feed it to a correlation with a local replica of the ranging code that you sent, and the correlation peak gives you an estimate of the round trip time of flight, and also you have your Doppler estimation from your Doppler block And from there, you basically get your range and velocity estimate. And DOA, same story, right? Either you read it back or you have some model of the beam scanner, which gives you the pointing angle of your laser, phi hat, theta hat. And now you have range, velocity, and DOA, and you can generate point clouds, which is your final LiDAR image. So that's basically the full picture for different types of LiDAR that we looked at. Questions? Okay, so that's it. Just to recap, so LiDAR, when it comes to 3D mapping, as of today, is the most capable type of sensor. So you get the nicest looking, highest resolution type of 3D maps out of LiDAR. Let's look at a quick video of something that's almost a state of the art as of today. This is a direct detection LiDAR we are going to look at. And this is just a point cloud. It's mounted on a car driving around. OK. For some reason, it's not going to full resolution. But here you see, and this is just, they're showing just one frame. So it's at 10 frames a second, I think. And it's not like overlaying multiple frames or doing slam or anything like that. As you can see, like things that are moving around, there's almost no motion blur. So it's a direct detection LiDAR. There's no velocity, but they get excellent reflectivity. And their basically color here is reflectivity at IR wavelength. So they get very nice, intensity or reflectivity out of this. Very dense. So this is a spinning LiDAR with 128 basically scan lines, uniform in elevation. So this is what you can, and it sees up to, I think, 200 or 300 meters, excellent resolution, high frame rate, and so on and so forth. That's the state of the art today. As you see, I mean, radar is still today way behind this, but LiDAR has its own limitations, right? So one is cost. These LiDARs today are extremely expensive. They're in, somewhere between, $5,000 to $20,000 range, depending on the specifics of the system one LiDAR. So very, very expensive. The performance, as we know, degrades significantly in poor weather because of the Mie scattering. So if there's fog, dust, rain, snow, those kinds of conditions can significantly degrade. And also, at least the direct detection type of LiDAR can be prone or quite sensitive to interference, either from other LiDARs or sunlight or any type of in-band interference can degrade. Some of these LiDARs, even if you have like two of them in close proximity operating, they kind of blind each other because of the strong interferences. So again, you can get beautiful 3D maps, very high resolution, and these are very capable systems. You also need to know the limitations, and that's why you need other types of sensing modalities for these limitations. Coherent LiDAR, as we know, you can get superior performance, and it's gaining more traction today. There are already commercially deployed coherent LiDARs, but not nearly as much as direct detection. Today, only FMCW is deployed. Hopefully, PMCW will be coming soon. Coherent systems today are even more expensive than direct detection. But again, there's lots of efforts underway to make it cheap, especially with better photonic integration. Hopefully, these systems can become cheap. They can estimate velocity, which is very, very valuable for autonomy. And that's one thing that direct detection doesn't do. And there's tons and tons of ongoing research on coherent LiDAR, especially PMCW, in terms of DSP, waveform design, hardware design. It's a very active area of research. One of, for instance, very interesting lines of research is that because you have the full complex field with the coherent LiDAR, you can be smart with your DSP and improve the performance in bad weather. And there's some very, very promising early research results that show you can improve a lot. And that's unique to coherent LiDAR because you need the full field to be able to invert some of these weather effects. Another one is advanced waveforms, as we saw for PMCW, for instance. They can help interference. They can make it more robust to Doppler, and so on and so forth. Fully solid-state LiDAR, which is a LiDAR with no moving mechanical components is considered the holy grail of LiDAR. Doesn't quite exist today. There's some versions of it with very limited performance, but a high performing like the one that we just saw, fully solid state LiDAR, does not exist today. A lot of progress has been made. Mostly, the last piece that needs to be solved is beam steering, right? Like a robust, high quality, high performing beam scanning solid state thing is still doesn't exist as of today, but a lot of progress has been made, and I'm sure eventually we'll get there. Something like optical phased array or something like that is needed to be able to do a fully solid state LiDAR. And again, we don't quite have it today, but I'm fairly certain we'll get there sooner or later. And that's it about LiDAR. Any questions? Yes.
Performance in bad weather can be improved by algorithms. I thought that's like the limitation of the wavelength.
Well, it's a limitation. So you still get all the one of the main problems is that false positives, right, that you get in bad weather because of the backscattered light. Now it turns out that if your algorithm is just a simple leading edge threshold, and you only have the intensity of the light, there isn't much you can do. You get a strong back reflection from a water particle, and it passes your detection threshold, and that's it. That's a false positive. But one thing, for instance, we can do with the coherent LiDAR. One is things like some information in the phase and the polarization can help you, distinguish, what the return was coming from. But also, if you capture the full wavelength, sorry, not the full waveform, instead of just applying a threshold, kind of try to extract more information from it in the sense, it kind of depends on the specifics of the waveform, but for instance, in a PMCW system, one of the artifacts that you get when there is fog in the weather is you get very specific patterns in these correlations, and then you can have smarter algorithms that learn those patterns. And so it could be some machine learning based algorithm, or even in classical DSP you can do very interesting things. So again, it's kind of like not just a DSP effect. It's kind of like a joint design problem of waveform plus DSP plus a bit of machine learning, and you can be much smarter in terms of how the whole system design is done. And then they can again, it's a I know my answer is a bit vague because it's an active research area, so I don't quite have like you do this and that and whether it's solved, but the results that people have shown is pretty impressive already in terms of what you can do. Yeah. Okay, so if there's no more questions, we can start the last chapter, which is about imaging and vision sensors or cameras. So this one is there's not a ton of DSP in here, although there's a little bit, but we mostly will talk about the physics and the system architecture of vision systems. As usual, we start with a bit of a history, then we talk about physics of imaging, lenses, we talk in detail about the digital image sensors, and then finally we finish with the system architecture of cameras. So what is imaging? Imaging is the process of capturing and recovering visual quantities from light. And what do we mean by visual quantities? So some of these quantities can be properties of the scene. For instance, an image can tell you information about the motion of objects. Color and reflectance, of course, is part of that visual quantities that you get out of images. It can even tell you identity of objects. You can classify different types of objects from an image. Or you can recover properties of the observer, and by the observer I mean the robot itself. You can recover some things like ego motion, like was the platform stable or static, or was it moving? And looking at, you know, a few frames of images from a video camera can tell you a lot about that. Or even the orientation of the robot can be deduced from images. And finally, you can get information about the properties of the medium. Things like scattering effects. As we know, fog, rain, and things like that immediately show in images, and we can, you know, get quite a bit of information about them beyond just, you know, the visual, you know, artifacts of the degradation in, say, contrast. You can actually extract physical quantities of the medium from images, or the types of light sources and things like that. Now, a lot of research in computer vision for the past, you know, 20 years has been focused in developing smart algorithms to process images from these vision sensors for extracting these types of, you know, properties that we just talked about. So computer vision is a huge field. I mean, you can teach multiple graduate courses, as we do here at Stanford, on computer vision, and we are not going to quite get to any depth regarding any of the specifics of the algorithms that are used to extract these types of information, but rather we'll learn about the physics of image formation and cameras and how they work. Okay, that's the main topic of discussion. Okay, so a bit of history. So photography or imaging started in the 1800s. One of the oldest surviving photographs is from 1826 by Joseph Nicephore Niepce. I hope I didn't butcher the pronunciation there, but it's called View from the Window at Lec, which this is the picture. I mean, by today's standards, it's a pretty poor image. And note that this one is a digitally enhanced version of the actual surviving image. So the actual one is much less contrasty than this, but nevertheless, it's a piece of history because it was the first time, you know, kind of like this imaging was done in a way that it actually survived. And how it was done was he used a material called bitumen of Judea, which is kind of like a natural asphalt material, which is photosensitive. So it kind of hardens as it's exposed to light. And it was a metal plate that was coated with that material, and then it actually exposed it for 8 hours. So it took 8 hours of exposure to get that. And then after the exposure, he had to, you know, wash off the unexposed coating with lavender oil and petroleum. So it was probably like a multi-day long effort to get just that one picture. So that was where it started. Shortly after that, Louis Daguerre invented a much better imaging, basically, system that became commercial, actually. So that was 1839. And the technique or the photographs that you get from it, it was called daguerreotype. It was widely used in the 1840s, 1850s, and the way it worked was it used silver halide on a polished metal, and then you would expose it to light, and then an image would form on the metal. You would get daguerreotype if they're done right, and it's difficult to do it right. You get images of exceptional quality. Even like best cameras today, digital cameras cannot beat daguerreotypes in terms of image quality. Here's an exceptional portrait of Abraham Lincoln done on a daguerreotype. And the trick was, I mean, there's lots of tricks in daguerreotypes, but they still required long exposure times, so the subjects need to, you know, stay perfectly still for minutes, sometimes less. Here in this picture, you would see, you know, there's a bit of a blurring on the thumb, and that means probably Lincoln got a little impatient during the process. But nevertheless, it's an exceptional image. Problem with daguerreotype is that you cannot make multiple copies. So you know, the original that you get, it's on a piece of metal, and that's it. You cannot, you know, it's not reproducible as in multiple copies. In about the same time, a different process was developed by William Talbot, which was from a commercial point of view, which was a much better imaging process. And that one is called calotype. And it's basically where the modern analog camera started. So it was done on paper coated with silver chloride. And you could get basically negatives from it. And from a master negative, you can do multiple prints, basically. So calotypes was a better process, and that's why daguerreotype eventually, got phased out, and calotype evolved into modern analog photography. Here's on the right, you see a calotype, which was captured in about the same time as the daguerreotype of Lincoln. And then fast forward a few decades, we get to the modern age of digital photography. So the digital camera was invented in 1975 at Kodak, which interestingly is a company that almost got bankrupt because they did not get the value of digital photography. So it was invented there, but they decided to not even announce it. And that's a picture of the very first digital camera. Interesting design. I don't know all the details, but it seems like they used a cassette tape as, to store the images, interestingly, which kind of makes sense. It was 75, so modern digital storage media didn't exist. But it wasn't until 1990s that digital cameras became commercialized, not by Kodak. Actually, Kodak almost entirely went down because they did not believe in the revolution of digital imaging. And then it was in the 2000s that, these technology start becoming cheaper, better performing, more robust, smaller form factor, and it started becoming suitable for, dynamic platforms like robots. So imaging for robotics kind of started in early 2000s. So this was like a super quick, history of imaging and photography. But we're gonna basically just go in depth and talk about the physics of image formation, and especially digital cameras, how they work. Okay, I think this is a good place to stop. Remember, this was the last in-person lecture, so there's going to be one more lecture which I will record and upload on Thursday, and so we will finish properly this chapter on imaging sensors, and that's it. Thank you.